I thought my last Steganography project was a total success. The script I wrote to hide messages in image pixels worked flawlessly. Or so I thought. It turns out the entire method I used had a problem, one that makes it kinda useless in the real world. And I didn't see it, but one of you did. A user left this comment. He pointed out that the LSB method I used would be instantly destroyed by JPEG compression. He said I needed to move my thinking outside of the pixel box and into frequencies, and suggested using discrete cosine transform or DCT. And he was right. So my new quest began to find a method that was truly robust and one that could actually make a hidden message survive JPEG compression, at least. But the path he suggested was a world of complex math that I was not prepared for. I started digging through research papers, and almost immediately my brain started to melt. I was seeing terms like Fourier analysis, frequency domains, quantization tables, and for a moment I really did think, this is way out of my league. But I stuck with it, and I realized you don't need to be a math genius to understand the idea. And the idea behind the discrete cosine transform is kind of beautiful. This method is all about separating the foundation of an image from its fine details. Think of it like a painting. When you look at it, your brain processes the big picture, the main shapes and colors, but also the fine details like the individual brushstrokes and the canvas texture. The discrete cosine transform is our tool to separate these layers. The script I wrote starts by breaking the image into tiny 8 by 8 pixel blocks. Then it applies the DCT to each one. And going deeply into this, the DCT converts the pixel data into the frequency domain. Basically, it reorganizes the data for each block into a new 64-number grid, separating the important foundational parts from the tiny textural details. The most important data, the low frequencies, are packed into the top left corner of this grid. Now these represent the overall shapes and brightness. They are so visually critical that changing them even slightly would create obvious glitches, which is a terrible hiding spot. The least important data, which are the high frequencies, are in the bottom right. These are the finest textures, basically digital noise. The problem is JPEG compression is designed to throw away data it deems unimportant, and these high frequencies are the very first thing to go. So if we hide our message here, it gets wiped out instantly. Another terrible hiding spot. This brings us to the core of the technique. Since the low frequencies are too visible and the high frequencies are too fragile, the solution is to not use the extremes. Instead, we target the mid-frequency coefficients right between visibility and fragility. And this is where we are going to hide our bits. So, how do we actually hide a bit inside one of these coefficients? In my script, I target a very specific spot, the coefficient at row 2, column 1 of each 8 by 8 DCT block. This position is chosen carefully. It represents a medium frequency, which is stable enough to survive compression, but also subtle enough that changes won't be visible. Now, you might wonder why specifically row 2 and column 1. This position sits in what's called the mid-frequency band. It's far enough from the DC coefficient at the top left to avoid visually critical data, but not so far that JPEG's quantization process will discard it. It's a sweet spot that researchers found balances in visibility with robustness. Different implementations might use slightly different positions, but they all target this same mid-frequency zone. The mechanism itself is elegantly simple. The script takes that coefficient and applies quantization, the same process JPEG uses. It divides the DCT value by a standard quantization factor and rounds it to the nearest whole number. This is crucial because we are essentially pre-quantizing the coefficients the same way JPEG compression will later quantize them. By doing this first, we ensure our bit modifications align perfectly with what JPEG will do, making our hidden message survive compression. Let's say after quantization and rounding, we get 42. Every number can be written in binary. The last digit in that binary form is the least significant bit, and it tells us whether the number is even or odd. If it ends with a 0, it's even. If it ends with a 1, it's odd. To hide a 0, we make sure the number is even. To hide a 1, we make sure the number is odd. If the coefficient's parity already matches the bit we want to hide, for example, we want to hide a 1 and the number is already odd, the script does nothing. The coefficient stays the same. But if it doesn't match, the script simply adds or subtracts 1 to flip the parity. For example, if the bit we want to hide is a 1, but the number is 42, in binary form it ends with a 0. The script adds a 1 to make it 43 because we changed the 0 to a 1, and we made it odd. Conversely, if we wanted to hide a 0 but the number was 43, it would subtract 1 to make it 42. Because we removed the least significant bit, which was 1, now it becomes 0, making it even again. And that's the entire mechanism. As we covered in the previous LSB video, the message length is embedded at the start so the decoder knows when to stop reading. Each coefficient's parity, whether it's even or odd, encodes 1 bit of the hidden message. The change is at most plus or minus 1. So when the image is reconstructed, the difference is mathematically tiny and completely invisible, just like the LSB technique from my previous video. But the core idea from that comment still lingered in my mind. Could an image with a message hidden this way actually survive JPEG compression? This was the entire goal, so I ran the definitive test. First, I used the script to hide a message inside a cover image, creating a perfect lossless PNG Stego image. Then came the real test, to simulate what happens when you share an image online. I took that PNG and converted it into a JPEG with a quality of 90. This exact compression step would have completely destroyed the message from our old LSB method from the previous video. I took that resulting JPEG file and fed it back into the decoder, and it worked. The message came out perfectly, not a single character out of place. The result of this new method, which is a form of DCT-based LSB steganography, was so good that I ran the tests again at even lower quality settings. Here is a direct comparison between our old LSB method and the new DCT method. This table says it all. The old method was incredibly fragile, breaking with any amount of compression. But this new DCT-based method succeeded. The hidden message survives the majority of common compression scenarios, like uploading an image to social media. Even at a low quality of something like 40, the DCT message was somehow still readable, with a couple of character errors, but the message was there. I should also mention what we're not covering here: detectability. While this method survives compression, a determined adversary using statistical analysis tools could potentially detect that an image has been modified. The parity changes we make create subtle statistical patterns. Now, for most casual use cases, this isn't a concern, which is something I wish to look into in the near future. So, the code that puts all this theory into practice is linked in the description below. I encourage you to check it out, play with it, and see what you can hide and retrieve even after compression. One thing to keep in mind as you experiment, the capacity is limited. With 1 bit per 8x8 block, that means 1 bit per 64 pixels. Or put another way, you need 512 pixels to hide a single byte. For a typical 1920 by 1080 image, that works out to about 4 kilobytes of hidden message space. Not huge, but more than enough for text messages, small files, or encryption keys. Maybe. And remember, this extraction doesn't require the original image. The decoder only needs the Stego image itself, which makes it incredibly practical for real-world use cases. Thanks for joining me on this adventure, and a special thank you to Makato, I apologize if I butchered the name, for that comment that sent me down this rabbit hole and inspired me to level up. It's proof that the best ideas often come from this community, and I'd love to hear your thoughts on this DCT method down below. And to finish, I just want to be clear. The math in this project was entirely new to me, and honestly beyond what I already knew. But messing around with it pushed me to check it out and learn more. And with that, I have to give huge credit to all the researchers and engineers who developed these techniques in the first place. All the resources I learned from were built on their work. This technique is quite a marvel, and it's incredible to realize that the DCT, the very foundation of JPEG compression technology, can also be used to cleverly survive it. Thanks for watching, and I'll see you in the next video.